I will speak about Equilibria games with algorithms. This is part of the IDT game theory and AI. It's a theoretical chair. What we don't do is pick software to play chess, but what we try to do is, for instance, to try to adapt methods from game theory to some AI problems, and also from a different viewpoint to use to study the consequences of the massive presence of AI in human interactions. Okay, so two very different adapt game theory tools to AI, and also study what the introduction of massive AI systems change in the human interactions. So I will not present here the thematics of the publication or pre-publications one by one. I think the last talk is already late, so I will jump to the picture of the people in the chair. It's a relatively small chair. We had Sebastian Jerchinovich with at ERT, Fabien with at TSC, two postdocs, Tommaso from Italy, who is now assistant professor at Ottawa. In Ottawa, Dana from Argentina, who is now assistant professor in Chile, and two PhD students, Etienne, who defended his PhD last Monday, and Mauricio, who will defend his PhD in December. Okay. So here I will just briefly present two papers from the PhD of the young guys. Okay. One for Etienne and one for Mauricio, and those the list of publication. So first, one chapter of the PhD of Mauricio, which is also joined with Fabien. It's about games played by exponential weight algorithms. So this is the idea is that for prediction or for decision making, machine learning algorithms are used more and more widely. As they are used more and more widely, they will interact. On where will this lead? And each of these algorithms that have been designed, in most of the cases, thinking of one person in front of some unknown changing environment, in front of the universe. But indeed, this universe is composed of other players who are maybe also using machine learning algorithms. Here, we focus on one particular type of algorithm, exponential weight algorithm, which is maybe the simplest and the elementary, the basic break, which is the most used. Very often, algorithms which are used, they combine in some way, in some bricks, parts of exponential weight algorithms. So let me be more precise and describe a bit the model of the algorithms. So suppose you are a player, you're an agent, and at every period, at every stage, you have to select one action, AT in A, and think of A being a finite set, and then only after selecting AT, you observe the current state of the environment, KT, and you receive a payoff, U, which depends on your action and also on the environment. What do you do? You know nothing about the law of KT. So what is the algorithm? It's very simple. You have a fixed parameter eta. It is based on positive weights. So every action will have for every period some positive weight, WTA, and at every stage you will play in a probabilistic way proportionally to the current weight. You will play according to the normalized weight. And how do you start? So you start with some initialization, and you update the weight with this formula, where you see where the parameter eta plays a role. And if eta is large, it means that you adapt very quickly to the current payoffs. And if action A would have given you a good payoff at stage T, you increase a lot the weight of action A for the next period. Okay, this is the algorithm, this is how you play. It has very good properties. For instance, one of them, you can prove this quite easily, that for every T and for all realization of the environment, what you have in average, what you get, this is your payoff, this is what you want to maximize, is at least what you would get by playing always the best constant action. And if you don't know this is achieving the maximum a priori. So you have the best you can have by playing constant action minus something which can be made small if you fine-tune eta with respect to t. Okay, so now we will put this together. Now assume that the environment is composed of other players who are also playing games. Nobody knows that he's playing a game, but it's composed of other players who are also using the same kind of algorithm. So we have a base game. We have some players from 1 to n. Each player has some set of actions AI and some player function which he knows. Okay, which depend on the actions of everyone. What is the behavior? Each player will use some exponential weight algorithm with some parameter eta I. It's important, there is no reason to think that they will use the same parameter. We also assume that eta does not depend on the stage, on the period number. And many papers do this, but here in practice, most of the time it's fixed eta. And also there is no reason to think that stage 1 for player 1 is the same as stage 1 for player 2. Maybe stage 1 million for player 2. And there is no period 0 indeed. So we're going to start anywhere which is possible. So what is the dynamics now? At every stage, each player will play some action, so proportionally to his current weight. And then you observe this is the actions of the other players, except from player I stage t, and you update your weight with the same formula as before, but now you put kt is the actions of the other players as stage t. Okay, so this is the model, very simple, but surprisingly, there was no result for this model. It's simple, it can be applied to many things, recommendation of movies, or suggestion of ads, or you can click or not, and many things. It's very simple and also very general. So let's define the normalized weight, the random variable of normalized weight, which is probability over AI. It is a Markov chain on the space of product of probabilities of action for every player. And what is the behavior of this Markov chain? Where can this lead? Does it lead somewhere? This is the question. So we have many results. I will present two of the two main results. But first I start with an example. Simple example which is meaningful. Let's say, here we have two players. Player 1 chooses the row, top or bottom. At the same time, player 2 chooses the column, left and right. This is the per period interaction. And the players, they get the same payoff. Either they coordinate on the diagonal, and they both get 1, they are happy. Or they don't coordinate, they are on the anti-diagonal, they get 0. But when you play, you don't know what the other is playing. So what happens here, if they run this algorithm, maybe not with the same eta, maybe with different initial weights, you can prove the following, which is a very positive result. What happens is, okay, maybe your stage 1 will play here, then here, then here, then here, but eventually, with probability 1, either from some station will always play top left, we will have coordinated with the algorithm, or from some stage on, we will always play bottom right. It looks very natural, okay, positive, but what? Not surprising, but notice that this is not true. For some others well-known, no inlet strategies. So it's a good property of this exponential weight algorithm. Okay, what can we say in general? Suppose it converges somewhere, where can it converge to? So here we introduce a definition, or we use the definition of weakly stable Nash equilibrium. Okay, it's a particular case of Nash equilibrium. So a situation where no deviation from one player is profitable, such that for every player I, whatever the other players play, you're indifferent between the different actions in the support of your probability distribution. For instance, in this game, we have two Nash equilibria here, which are strict Nash. Every deviation is strictly unprofitable. And also a continuum of weakly stable Nash equilibrium, where player 2 plays right, and player 1 mixes between top or bottom with this condition. What we can show is that in any game, for any number of players, if we converge with positive probability to some random variable, to something, that this something has to be a weakly stable Nash equilibrium. And so it strongly shows up this notion here for these games. As a corollary, for some games, there is no existence of weakly stable Nash equilibrium, so there is no possible convergence on something zero-sum game like matching pennies. So here we can do other things, but it will not converge, we are sure, because of the first result. The second result is not about some definition of some points which show up strongly. It's about the probability of playing a thick Nash equilibrium tomorrow, given where we are today. You can look at this variable. Okay, so define LT, it's a probability, it's a number between 0 and 1, it's a random variable, to play a thick Nash equilibrium at period t plus 1, given what we know at period t. And we can prove some kind of 0-1 law that it will always convert this LT to a random variable, but now with values in either 0 or 1. Either the probability to play a thick Nash will converge to 1, or it will converge to 0. It cannot do anything else. It cannot converge to one set. So for instance, it's a game we have seen before. Here, this is the space where the Markov chain lives. Either we converge to one of the thick Nash, the red points, or we'll stay forever in the green set, the green one-dimensional set, which contains the weakly stable Nash. In this example, another example, we have only one thick Nash, and here you can show that depending on the weight, initial weight, and the parameters, you will, with some positive probability, you will converge to this point, and with a complement probability, you will always stay in this square, and you will not converge. So it doesn't imply that you will always converge to something. Here, with some probability, you will converge and will always play this from some stage on. With some other probability, you will circulate here forever. Okay, this was the first paper from the PhD of Mauricio. Definition of weakly stable Nash equilibrium would strongly show up, and this theorem which says that the probability to play a thick Nash in the sort of a good outcome tomorrow either converges to 1 or converges to 0. Let me now go to the second part. With Etienne. So now with the opposite approach. We start with some optimization problem. Like in robust optimization, we often have things like this. We want to minimize the supremum of the function. There are many possibilities to study a problem like this. Here we consider what we call the game theoretic approach, which can work under some conditions, not always, but this is one approach. Consider the zero-sum game, so a game where simultaneously player 1 chooses some point in x, player 2 chooses some point in y, and g of xy is the payoff of player 1 minus the payoff of player 2. Player 2 pays g of xy to player 1. Okay? Suppose this game has a Nash equilibrium, because it's zero-sum is the same as a saddle point. So this is the definition. Then it's a very simple lemma to show that y star will do the job, which will solve this problem here. Okay. Example in GANs. Okay. I'm not going to explain in detail this picture, but in GANs, indeed, you model it as a game between a generator and a discriminator, and you need to solve this problem, and you need to find the parameters of a neural network for the generator, achieving this minimum here. Okay. And what is done is the game theory approach, try to find the saddle point of this game. So how do we do this? So suppose G is nice, here I'm not very precise, that we have a saddle point. How to find a saddle point? So it's, I believe, an important and difficult problem. The first idea in natural is to look at a gradient descent ascent. So player 1 wants to maximize G, so you can use a gradient ascent, player 2 a gradient descent because he wants to minimize G. But it is well known that it doesn't always converge, you can spiral away from a cycle and you can diverge. So one of the many options to correct this is to use the optimistic variant, what is called the optimistic variant, where you add a term from stage period t minus 1 here. So plus 2 eta, you do the same, but here you correct it so that instead of spiraling out of the cycle, you go inside, and then here you will converge to the center of the cycle. Okay, for the presentation, okay, I've shown you the nice formula for the gap, but for the presentation, we'll look at a very simple case of player function, which is a bilinear case. In mathematics, very often we start with linear functions when we want to look for something. Here in games, we start with bilinear. So the point here is that it's really to study how some algorithms perform on a very simple game that could be solved by other methods. So, first result, in the segment of the theorem is 2 pages, but here is like a summary. What will play a role, an important role, is this quantity. So the largest eigenvalue of A transpose and the smallest positive value of A transpose. So we characterize the range of parameters eta, the exact range, where we have convergence. And then it converges to Nash equilibria, and which one, we know exactly which one this is. We can characterize it. This convergence is quite fast, it's exponential, and we compute the exact rate lambda of eta. Knowing this, that we can optimize in eta, and we get the optimal rate lambda star. When you minimize this in eta, you have something which is strictly less than 1, of course, but it's always at least square root of 2 divided by 2 as a function of mu max and mu min. So here it's like we, surprisingly, and this was not fully done, some were done, but not all, and so we improve on the existing literature. Now, we are game theory, so we want to see what happens for more games. So we go to general sum games. We can do the same, but instead of having a payoff g for player 1 and minus g for player 2, let's look at 2 different payoff functions. Okay, so suppose now A is a payoff for player 1, and B is a payoff for player 2. So player 1 he wants to maximize this. At the same time, player 2 he wants to maximize this. In a nutshell, theorem 2, a bit simplified. Here, it is not true that it will always converge, even if eta is small. Okay? But we have some conditions, sufficient conditions for convergence. And interestingly, in somehow large class of games, we can show that either will converge, and if we converge, the limit will be a Nash equilibrium, or both payoffs would go to plus infinity, which can be considered as a generalized Nash equilibrium as a very good outcome for the players. Okay, so this is what the games are payoff plus infinity. So this is kind of interesting to introduce this variant for general sum games. But now, okay, what have we done? I've told you we start, the problem of interest is a mean sub problem. So let's summarize what we can do, what we have learned. So we want to solve this. So we can run OGDA, optimistic gradient descent ascent, for the zero-sum game with some size eta. We use theorem 1, and we know now the convergence rate, the exact convergence rate. Option 2, we do the same, but now we can optimize eta if we have some knowledge about this parameter, some bounds. We can optimize eta to get this optimal rate. I don't tell you what is beta, but it's related to this ratio. Option 3, and this is the main novelty of the paper, of the approach. You can run the algorithm, but not for a zero-sum game. You keep the same payoff for player 1, but for player 2, you use this payoff. You choose this payoff where A plus is the inverse of A when it exists. If not, it's a generalized Morpendroz inverse. And I think it's A minus 1. You take this. And you choose eta is 1/2. Very simple. Then we can show that YT will converge to the same limit as option 1 and 2, but with a rate which is much better because it can be square root of 2 divided by 2. It's the optimal weight here. You can have it for any matrix if you know how to derive this B matrix. So this option 1 is the blue line, the speed of the blue line, option 2 is the red, and option 3 is the green. Okay? So what we see here is that introducing appropriate general sum game can speed up a problem, a min-match problem or a min-sum problem. But now this is very simple. It was only for linear games. It's nice to know this. It's important to know this. But what can we do for the game or general game? Suppose we have a game like this. Okay, it's too restrictive, but any polynomial game can be written like this. And then it's a whole story because with any polynomial game, you get almost all games. Okay, you can do the same trick. You can run the general sum extension of OGDA of the game with payoff G for player 1, and for player 2, instead of having G2 is minus G, you can use this the same minus A plus. transpose. Okay. For instance, suppose you have this payoff function, and you want so your problem is mean sup of this payoff. Okay. So here you can write it in this form with this psi in this phi on this matrix A, and then G2 instead of minus G, you will get this very simple formula function. This 2 instead of being minus 2 becoming 2, it becomes 1/2. This 1/3 becomes minus. They have the same Nash, the zero-sum gain on the appropriate general sum gain, but the speed of convergence is much better if we use the general sum variant. And this is one of the main message here. So one is that it's very common using like optimistic variant when you have to compute equilibria of gains, not only gradient descent ascent. But this is already, let's say, quite known. But what is really new is that running OGDR and an appropriate general sum gain improves the convergence of two equilibria of a mean sup problem. And I think it's already late. I will stop here.
Thank you very much. So, questions? I have a small question. So here you're playing with constant learning rates, and have you tried to play with to see the convergence rate can be improved by playing with learning rates that would vary along situations? So that you have to do if it makes sense to.
Yes. It perfectly makes sense in both papers to look at what eta vary this time. In the first one, we don't want to do this because in practice, this is not what people do. And there is no reason to think that it will work if you fine-tune eta with t, but at the same speed with the players. And we don't think there is a reasonable reason. It's not reasonable to assume this. And why it will be in square root of t for player 1, and player 2 will also be in square root of t with the same t. So it can be very different time period. So this is not true.
What way to express the learning rate independently?
Yes, what they do in practice that you fix eta, you do something, you train it, and then you change eta, fix, and you try, and then you learn, and then you stick to some eta. Okay, which is a bit different. You have other results. In the case where eta t decrease in some nice way, for instance, you can prove that in potential gain, generic potential gains, if you decrease in a nice way altogether, you will converge to a Nash equilibrium. This can be proven, and this was already done. For the second thing, yes, you can always do. This is different because here you want to compute a Nash, but here you're the one you choose your eta. No, I think here you will never go below square root of 2 divided by 2. So the option 3, I think you cannot beat it. In my thinking, again.
Thank you. More questions? Yes, actually. Please, how you help us to relate over to period one, right? With the question you have asked the period.
Okay. So this means I've not been clear enough.
Oh, please direct.
So one question, what happens when we all use machine learning algorithms? So this was relating to the first paper, okay? We have all placed some, here we have chosen exponential weight algorithm, and of course, be good. There are many things we still don't know of this model, but it will be good to generalize why all players use the same exponential weight, maybe, and there are also variants. But what happens in this case, where each player in a game using, instead of saying I play a best reply, I try to understand what the other do, like it's done usually in game theory, using some fixed algorithm which was designed for one player against nature. Okay, so we look at the interaction of players using algorithms. This was the first one. The second one is how game theory, like say thinking or method, thinking of a game, can help to solve some mean-sup problem, which happens, for instance, in GANs. Okay, in many robust optimization problems, you want to minimize the supremum of something. So there are many methods. This is one of them, which is based on game theory tools.
Thank you. Okay. Yeah. So if no more question, Thank you very much.